Let's start with something a little easier. Slope of a tangent line at a particular point. So imagining that instantaneous slope at a point. There we've got a positive slope. Here we've got a negative slope, and here we've got a slope of 0. The next problem wants us to write the equation of a tangent line when x equals 2. And luckily, both of the information that it gives us is for when x equals 2. That's what we need. So what this tells us is that when x is 2, y is 3. That's our point 2, 3. What the other one tells us is that at 2, there's a slope of -1. That's what the first derivative tells us, that instantaneous rate of change or slope. So we have a slope of -1. We know when x equals 2, it's going through the point 2, 3. With point and a slope, we can write the equation in point-slope form. You could leave your answer like this, or you could solve for y. Doesn't really matter, but if you keep going, make sure you're really confident in your answer. Otherwise, I would just leave it. So same idea here. Find the equation of the tangent line. And we know that we know the equation for f of x this time. And we want the equation of the tangent line when x equals 2. So the first thing we need to do is find the slope when x equals 2. Because to write an equation of a line, we need to know the slope and we need to know the point. Well, the point is going to start with a 2 because we want to write the equation when x equals 2. To find the slope when x equals 2, first we need to find that first derivative, because that's what helps us find instantaneous slope or slope at a point. So because we want it specifically at 2, when x equals 2, we're going to plug in 2 into this equation we just found for the first derivative to get that our slope at 2 is 2. Now we need to finish our point. So I need to actually figure out what is f of x at 2. So I'm just going to plug in 2 into the original function to figure out what the output is when 2 is the input. We're looking for our y value. And we get -3. So with the slope and the point, now we can go ahead and write our equation in point-slope form. You can solve for y. You can make it solve for y even more than that. But again, you can leave your answer. Don't oversimplify it. The next thing we're trying to do is to differentiate. We're just taking the derivative. We do need to use the quotient rule on this one. And so our quotient rule is low d high, so low times the derivative of what's on top, minus high d low, or the derivative on the bottom, over the square of what's below. So what's below squared. I'm going to simplify this a little bit. Just using the distributive property there in the numerator. Next, I'm going to combine like terms in the numerator to get -3x squared plus 3. But then we can see that we have a GCF. And if I want to keep going, x squared minus 1 is x plus 1 times x minus 1. But from here, we can't really do anything else from here. So I would leave it like that. Or again, you could leave it, any of these, you could leave it as. But for multiple choice, this final answer is probably what you would be looking for. All right, number 6. First, we're going to find the average rate of change on the interval 1 to 4. So when it gives you an interval, it's giving you the x values. So from when x equals 1 to when x equals 4, find the average rate of change. And remember, at rate of change, when you hear that phrase, we're just talking about the slope. And since we're not talking about instantaneous rate of change here, we don't need to find the derivative of anything. So to find the slope of a line, right, our slope formula from way back in Algebra 1 is just the change in y over the change in x, or y2 minus y1 over x2 minus x1. But to use that formula, we need to figure out our y values. We have our x values, we need to figure out our y values. So when I plug in 1 into the equation, we have 1 plus 2 over 1, so 3. And then when I plug in 4, I get 64 plus 2 over 4. So let's see, 66 over 4, 33 over 2. Probably just leave it 33 over 2. And then I'm going to use my slope formula. So 33 over 2 minus 3, I'm going to write that 3 as 6 over 2. All over 4 minus 1, so it got a little messy. 27 over 2 over 3. So if I have 27 over 2 divided by 3, that's the same thing as 27 over 2 times 1/3. 27/6 is 9/2. So my average, my average rate of change there would just be 9 over 2. But now we're going to find the instantaneous rate of change at 2. When we're talking about instantaneous rate of change, that's when we're talking about finding the first derivative. So of our original function f, if I need to find the first derivative, what I would probably do first is rewrite f as t cubed over t is t squared, and 2 over t is the same thing as 2 times t to the negative first. So I would rewrite it like this first so that I can use the power rule. Or you can use the quotient rule here, but I like the power rule if I can use it. So when I take the derivative of t squared, I get 2t. And then here I'm going to get a negative 2t to the negative second. And let me rewrite that answer before I plug in the 2. So I have 2t minus 2 over t squared. Then I'm going to plug in the 2 to get my instantaneous rate of change. So 2 times 2 is 4, minus 2 over 4. So 4 minus 1/2 is 3 1/2, or 7/2 for our instantaneous rate of change. So average rate of change, you're finding the slope. Instantaneous rate of change, when you're finding the instantaneous slope, find the derivative first, and then plug in the point where you're trying to find that instantaneous rate of change. Number 7, h of x is g of x over f of x. So right away, I know that we are going to need to use the quotient rule in this one. So quotient rule is low, which in this case is f of x, d high, this is to find the derivative. So derivative of the high minus high d low, derivative of the bottom, over the square of what's below. And in this case, we're finding we're finding it at 2, h, the derivative of h at 2. So I'm going to plug in 2's for all of these. And all the values that are needed are given. So f of 2 is 5. G prime of 2 is -1. G of 2 is 3. F prime of 2 is -2. And then in the denominator, f of 2 is 5. And we are squaring that. So let's simplify this a little bit more. We have -5 plus 6 over 25. Our answer is 1/25. All right, the next one, we're finding the values of a and b so that f of x is differentiable. So not just continuous, we want it to be differentiable at x equals 1. So in order to be differentiable, first we do need it to be continuous. And in order for it to be continuous, we need these two functions to equal one another when x equals 1. So if we need them to equal each other when x equals 1, I'm going to go ahead and go through. Actually, I'll just go ahead and plug in a 1 for x. So what this would look like is we have 1a, or a, equals b times 1 squared, or 1b, plus 1 is a plus 2. So we know that a needs to equal b plus 2. This shows us how to make them continuous at x equals 1. Because to be differentiable, they need to be continuous. And if I wanted proper notation here, I probably should have done that. So like the limit as x goes to 1 from the left, we'll do the left side of f of x. That was the left side. We ended up just getting a. And then that needs to equal the limit as x approaches 1 from the right side of f of x, which we need to be b plus 2. So that's why we need the a to equal the b plus 2. But we also need it to be differentiable at 1. And to be differentiable at 1, that means we need f prime of x. So same idea. We need the limit as x approaches 1 from the left of the derivative to equal the limit as x approaches 1 from the right of the derivative. And so remember, if these don't match up, that's what creates either a corner or a cusp, is when the derivatives don't match up perfectly at a point. For it to be differentiable, the limit needs to be the same. It needs to be equal. It needs to be approaching the same value there. So we're going to take the derivative of each one of these functions next. So from the left, the derivative of ax is a. And on the right, our derivative would be, let's see, 2bx plus 1. And again, our x is 1 here. So if I plug in a 1 for x, that just means that it's going to be 2b plus 1. I should probably be a little bit more careful with my notation. But basically what we have then is we know a needs to be b plus 2 because in order for them to be continuous. And we know a needs to be 2b plus 1 in order for it to be differentiable at 1. So we needed the functions to match when we plug in 1, and we needed the derivatives to match when we plug in 1. So if both of those things need to be true, now we have a system of equations that we can solve by either using substitution or elimination or by graphing. I'm going to use substitution here because we have a equals and a equals. That means we need b plus 2 to equal 2b plus 1, which means that we need b to be 1. And if b needs to be 1, if we plug in 1 for b, that means that a needs to be 3. So our answers would be b equals 1 and a equals 3. That's one of the tougher ones on here. For this one, we need to know the derivative definition in order to know which one of these match. And there's a few different definitions that we've done. The one that we've used the most is the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, which ends up just being the h, right? But here it's set up a little bit different. Instead of h approaching 0, we're saying the change of x is approaching 0. And so it's the same thing as what we practice. It's just all of the h's are being changed in notation to the change in x instead. Same idea though. So if you remember how we do this, it means that first we plug in x plus the change of x in for x in our function. So when I do that, I would have, in this case, f of x is 2x squared plus 4, so 2. And then instead of x, I'm going to write x plus the change in x squared plus 4 minus, now I'm going to do f of x. F of x is just that original function, 2x squared plus 4, all over the change in x. And then we're just looking for the one that matches, and in this case, that would be C. H of x equals f of x times g of x. That's the product rule. So product rule is we take one times the derivative of the other plus that second one times the derivative of the first. All right, and we're doing everything at 2 here. So f of 2 times g prime of 2, or the derivative of g at 2, plus g of 2 times the derivative of f at 2. So everything is at 2. So where are my 2? So here's g of 2. Here's f of 2. Okay, so f of 2, I'm just going to make a list of what I know. F of 2 is 2. Our value at f is 2. Our value at g of 2 is negative 3. F prime of 2 means the slope at 2. F is the blue function, so the slope at 2, the slope of this line looks like negative 1. And the slope of the g graph at 2 looks like it's 2, up 2 over 1. And then we're just going to plug in what we know there. So f of 2 was 2. G prime of 2 was also 2. G of 2 was negative 3. F prime of 2 was negative 1. So we have 4 plus 3, which is 7. Same picture, different question. What is g prime of 3? Or in other words, what is the slope at 3? Well, we have a corner at 3. 1, 2, 3. Yeah, at g, we have a corner at 3. And so it is not differentiable there. That is not possible. It does not exist. All right, let's see here. We are watching ducks hours after 9 a.m. So this first one is referring to 9 a.m., 0 ducks. And then the first hour, it looks like there were 3 ducks. Then after 2 hours, there were 8. Okay. So for part A, determine the average number of ducks which have crossed the road per hour during the 7-hour observation. Okay. Average number of ducks. So we're not looking for an instantaneous change of ducks here. We're looking for an average. We're just finding the slope over the whole time. So we're looking for the change in ducks over the change in hours. So total number of ducks changed by 28 over the 7-hour period. That means there were 4 ducks per hour. We averaged 4 ducks per hour. So if we want to estimate the value of the slope at 4.5, so obviously there is no 4.5 here, but we can estimate it by looking between 4 and 5. So now I'm just going to find the slope between 4 and 5. So 21 minus 12 over 5 minus 4. So that would be 9 ducks per hour at that time of day. Apparently ducks are really popular right then. So this one's a little trickier too. We're using that limit definition at a specific point because we're also looking for our C value here. So and we're thinking backwards. We're wondering what was the original function if this is what it looks like when we plug it into the limit or the derivative definition. And so what was the original function? And also, what is the value that we plugged in? What's that C value? Because the C value is going to tell us, like, how did we get this negative 14 right here? Right? Because the derivative definition that we're looking at here, when it's at a specific point, was like the f of x minus the f of c. So in this case, we are plugging in, well, at the change of x. So I guess it would be like the f of x plus the change in x minus f of c. So let's see here. We have, this is what we're plugging in for x. So that's where our x is going to go. So what our function would say, if this is my x value each time, my function would be 2x cubed minus 2x minus 2. This limit definition isn't right. 2x cubed minus 2x minus 2. And what we're plugging in, our C value then, is that negative 2. That's where that negative 2 is coming from. And you can check your work if you're not sure if you did this right or not. And if I plug in negative 2 for my x, I should end up with this negative 14. That's our f of c right there. So if I plug in negative 2, let me make sure I did this right. 2 times negative 2 cubed minus 2 times negative 2 minus 2. That's so many 2's. All right, so we get negative 16 plus 4 minus 2. And that's negative 14. Praise. We did it right. So you just kind of have to imagine what they're substituting for x. And then stick an x there instead. 2x cubed minus 2x minus 2. All right, we've got a table to look at. We're finding the derivatives. This first one, we're finding at negative 1. We don't need the product rule or quotient rule here. We just need to find the derivative. If we're finding the derivative of this, we're taking 3 times the derivative of f minus the derivative of g. We just do them separately. When you're adding and subtracting, you just find the derivative separately. So 3 times the derivative of f at negative 1. So the derivative of f at negative 1 is 2. So 3 times 2 minus the derivative of g at negative 1, which is 1. So we get 5 as our answer there. Next one, we are using, same idea, we're using the product rule though. So in my product rule, I have 3 times f of x times the derivative of g plus, this time we're taking g of x times the derivative of the first, which would be 3 times f prime of x. All right, so, and we're doing all of this at -1 again. So 3 times f of -1 is 0, times g prime at -1 is 1, but we really didn't need to do that because that's already 0 anyway. So all we really care about is this section. G of -1 is -1 times 3 times f prime at -1 is 2. I'm just using the table there. And I'm getting -6. 0 plus -6 is -6. So you just need to know the product rule for that one. For this one, we just need to know the quotient rule. So our quotient rule is low d high minus high d low, and when I take the derivative of the denominator, it's, wait, I didn't do that right. Sorry, low d high minus high is just f of x. Derivative of the bottom is g prime of x, because the derivative of 2 is just 0, so we don't need to include that when we're finding the derivative of the denominator, over the square of what's below. All right, and then we're plugging in 0 for all of these. So I'm going to go ahead and replace all of those x's with zeros. Okay, so first thing, we're finding g of 0 plus 2. So that's -3 plus 2 is -1. Times f prime at 0 is -2. Minus f of 0 is -1. G prime at 0 is 4. And then in the denominator, I have g of 0, which is -3, plus 2 squared. So let's simplify this. We have 2 plus 4 over -1 squared is 1. I'm getting 6 again as my answer. All right, last one. This is a graph of the derivative function of f. So this is not f. This is the derivative of f, the slope, right? We're graphing the slope of f here. What are the values of x for which f, the original function, has a horizontal tangent line? So I'm not going to try to sketch f for a second. I'm just going to sketch a random function for a second. If we have a random function, they have horizontal tangent lines at these relative maximums and minimums. If this was like f, it's not, but let's just say it was. So our slopes at all of these horizontal tangent line, right? If it's a horizontal tangent line, that means our slope is 0. And so what we're looking for is we're looking for where the slope is 0. And so if this is the slope function, the derivative function is graphing the slopes. If I want to know where the slope is 0, I am looking for literally where the value of the graph is 0, where it crosses 0. So there's one here at 4, here at 2, and here at 0. So don't worry so much that there's a cusp right there at 2, because remember, this is not the original function f. This is the derivative function. So a cusp means that the derivative of the derivative function doesn't exist, but our actual derivative does exist here because this is the derivative function and there's a point there. So all we're looking for here is where the slope is 0, and the slope is 0 when the value of the derivative function is 0. So our answers would be 0, 2, and 4. The reason we would not include this -2 way over here is because that's just the start of the graph. And so there wouldn't, if that's where your graph is starting, there wouldn't be a relative maximum or minimum there. It's just the start of it. And that's all.